Today, we're going to explore what would happen if Einstein's theory of relativity were wrong. Specifically, we're asking, what if time didn't slow down at high speeds? Our topic today is GPS. Many people still find it hard to believe that moving faster, especially close to the speed of light, makes time pass more slowly. But the GPS system we use every day is living proof that relativity works. So let's imagine for a moment that it didn't. Let's imagine a world where time behaves just as Newton thought it did. Absolute, universal, and unaffected by how fast you're moving or where you are in a gravitational field. At first glance, that might sound like a more comfortable, simpler universe, but it would fundamentally break one of the most reliable technologies we depend on every day, GPS. Every time you use your smartphone to find a coffee shop, every time a rideshare driver navigates to your pickup point, or a shipping company tracks a cargo container across oceans and continents, GPS is at work. It's embedded into our transportation networks, our emergency services, and even the electrical grids that power our cities. But none of this would function as we know it if Einstein had been wrong about relativity. To understand why, let's zoom in on how GPS works. The system relies on a constellation of at least 24 satellites orbiting the Earth, each carrying an extremely precise atomic clock. These clocks aren't just accurate, they're so precise that they lose only about 1 second every 100,000 years. The basic principle is simple. A GPS receiver on Earth listens to the signals from at least 4 of these satellites. Each satellite broadcasts the exact time it sent the signal. By calculating how long it took for each signal to reach the receiver, the GPS system determines how far away each satellite is. With 4 distances from 4 known locations, your device can triangulate your precise position, latitude, longitude, altitude, and even speed. But here's the catch. This method only works if the clocks on the satellites and the receiver on Earth are perfectly synchronized. And that's where Einstein comes in. The satellites orbit the Earth at about 14,000 kilometers per hour, roughly 3.9 kilometers every second. That's fast. Fast enough that time dilation, as described by special relativity, begins to kick in. According to special relativity, a clock on a fast-moving satellite will tick more slowly than a stationary clock on Earth. This isn't just theory, it's measurable. The satellite clocks tick about 7 microseconds per day slower due to this effect. A microsecond is 1/1,000,000th of a second, so 7 microseconds may sound negligible. But let's put it into context. Light travels about 300 meters in 1 microsecond. So if your GPS is off by even 1 microsecond, your position could be off by 300 meters. An error of 7 microseconds? That's 2.1 kilometers of error, just in one day. But we're not done. General relativity also affects GPS. General relativity tells us that time passes faster when you're farther from a source of gravity. Since the satellites orbit about 20,200 kilometers above Earth's surface, they experience a weaker gravitational pull than clocks on the ground. That means, according to general relativity, the satellite clocks actually tick faster, by about 45 microseconds per day. So let's do the math. Special relativity says the clocks should tick 7 microseconds slower. General relativity says they tick 45 microseconds faster. Net effect? The satellite clocks tick 38 microseconds faster than clocks on Earth. That's 38 millionths of a second per day. Now, if you ignore that 38 microsecond difference and pretend that time is absolute, if we lived in a Newtonian universe, what would happen? Your GPS would be wrong by about 11.4 kilometers after just one day. That's the length of about 110 football fields. If you were navigating in a city, you could end up in the wrong neighborhood. If you were a commercial airline relying on GPS to guide your descent, you could be several kilometers off target. For a military missile system, the consequences would be catastrophic. And for autonomous vehicles, forget it. They'd be navigating blind. But the GPS system isn't broken. It works incredibly well. And the reason it works is because engineers built it assuming that Einstein was right. They built in corrections to account for both the slowing of time due to speed and the speeding up of time due to altitude. Without these adjustments, without relativity, GPS would be useless in a matter of hours. There's more. Engineers have actually run tests. They've turned off the relativistic corrections in simulation. The result? The positional errors begin to accumulate almost immediately. Within minutes, your location is unreliable. Within a few hours, it's off by several kilometers. After a day, it's chaos. And the effects of relativity aren't just academic. They've been tested with real hardware. In the Haffel-Keating experiment of 1971, scientists took 4 atomic clocks and flew them on commercial airliners around the world. When compared to synchronized ground-based clocks, the airborne clocks showed time discrepancies that matched predictions from relativity. The clocks going east lost time. The clocks going west gained time. These weren't just tiny differences. They were exactly what Einstein's equations said would happen. So, what if relativity were wrong? What if time didn't slow down with motion and clocks weren't affected by gravity? Then, none of this would work. Not the GPS satellites, not the atomic clocks, not the positioning algorithms. You would open your phone, try to find your way home, and the little blue dot would send you to the middle of a lake or a highway overpass. And remember, this isn't just about phones. Cell networks use GPS timing to synchronize towers. Stock exchanges rely on precise timestamps from GPS to validate transactions. The electrical grid uses it to coordinate phase across long-distance lines. If relativity were wrong, our entire technological infrastructure would suffer. Now let's flip the question. If relativity were wrong, and yet GPS still worked, we'd be in a scientific crisis. It would mean one of two things. Either our entire understanding of time and gravity is flawed, or there's some unknown mechanism keeping everything in sync in exactly the way Einstein predicted, purely by coincidence. That would be far more unsettling than simply accepting that the universe works the way Einstein described. Think about this. Satellites don't carry clocks that are 38 microseconds fast on purpose. Their clocks are designed to tick at the same rate as those on Earth. The 38 microsecond difference is a natural consequence of where they are and how fast they're moving. It's a physical effect that happens automatically. The only thing engineers do is program the system to account for it, because they know it's real. Imagine a factory where every machine depends on perfect synchronization. If one machine starts running just a little faster or slower, the entire line falls apart. That's the GPS system. And relativity is the master clock that keeps everything running smoothly. So next time you open your phone and watch your location, pin drop precisely on your street corner. Remember what made it possible. Not just satellites, not just software, but 100-year-old insight into the nature of time and space. Einstein didn't just change physics, he enabled the world we live in. And in the end, the greatest proof of relativity isn't locked away in a lab or a chalkboard. It's in your pocket.